Today, we are diving into a huge, and I mean huge, question. How do we build AI that's actually safe? And the answer, believe it or not, doesn't start with code. It starts with the basic rules of the universe itself.
So let's just start right there. How on earth do you get a universe packed with galaxies, life, and consciousness from just a few simple laws of physics? Honestly, it feels like a magic trick. But, as you're about to see, the trick is way simpler than you'd think.
You know, the secret recipe for everything really only has two ingredients. First, you've got building blocks. Think of things like atoms, or bits of data, or even Lego bricks. And second, you have rules that tell them how to interact, like the laws of physics or grammar, or an algorithm. And with just those two things, you can build, well, pretty much everything.
This whole process has a name. It's called emergence. It's where a group of simple things gets together and suddenly develops properties that none of the individual parts have on their own. Just think about it for a second. A single water molecule isn't wet. A single ant is kind of dumb, but a whole colony is incredibly intelligent. A single neuron can't think. The magic isn't in the individual bricks. It's all about how they come together.
Okay, so let's see this magic trick in action. We're going to use something called a cellular automaton. All it is a line of cells, and each cell is either black or white. Now, we apply one ridiculously simple rule. A cell's color in the next row down is decided by the three cells directly above it. That's it. That is the entire program. So, what do you think happens when we let it run?
You get this, a whole universe of just mind-blowing complexity. It's filled with structure and randomness, patterns that are totally impossible to predict just by looking at that one simple rule we started with. This specific pattern, by the way, comes from something Stephen Wolfram called Rule 30, and it's the perfect example of emergence. Simple rules can create an incredibly complex world.
In fact, Wolfram went ahead and sorted all these different behaviors into four main classes. You've got class 1, which is, well, it's just boring. It goes flat right away. Class 2 is repetitive, like a crystal pattern. Class 3 is just pure chaos, like a bunch of gas molecules bouncing around. But class 4 is the sweet spot. It's this incredible mix of order and randomness, right on the edge of chaos, and it's where all the really interesting stuff like life and intelligence seems to happen.
So this leads to a pretty logical question, right? I mean, if the rules are so simple and the whole system is deterministic, can't we just, calculate the outcome? Shouldn't we be able to predict the future of that pattern perfectly?
And the answer is a hard no. And this, right here, is one of the most profound and frankly kind of unsettling discoveries in all of modern science. For a lot of these complex systems, perfect prediction isn't just hard, it is fundamentally, mathematically impossible.
This brings us to a really mind-bending idea, computational irreducibility. It basically means that for systems like Rule 30, there is no shortcut to the future. There's no fancy equation you can use. The only way to know what it's going to do a million steps from now is to actually run the simulation, step by painstaking step. The journey is the destination. The process itself is the only answer.
And believe me, the prediction problem gets even harder from there. You've got the butterfly effect, where one tiny little change at the start can lead to a completely different future. And then there's something called a combinatorial explosion, which just means the number of possible outcomes is often bigger than the number of atoms in the entire universe. So yeah, perfect prediction is it's off the table. So why does any of this matter? Why are we talking about these digital patterns? Because this isn't just some abstract theory. This is the absolute beating heart of the AI alignment problem. We are building these incredibly powerful AIs that are Class 4 systems, and that means by their very nature, they are computationally irreducible. We cannot fully predict what they're going to do.
This new reality really forces us to make a choice. When we build these powerful new things, are we going to be an architect with a perfect blueprint and total top-down control? Or are we going to be a gardener, someone who prepares the soil, nurtures growth, and accepts that they don't know exactly how the plant is going to turn out?
Well, with AI, the architect approach is already failing. The way we do things now, like reinforcement learning from human feedback, is basically trying to give the AI a simple blueprint. We give it a reward it should try to maximize based on what humans say they like. But this just doesn't scale. It can't possibly capture the richness of human values, and it's trying to force a simple solution onto a fundamentally unpredictable system.
It really just boils down to one simple, unavoidable truth. You cannot be an architect for a system you cannot predict. It's impossible.
If you can't know for sure what the building is going to look like in the end, you can't write the blueprint. And with AI, we are essentially flying blind. This means we have to start asking a totally new kind of question. The one you see here just frames that shift perfectly. We've got to stop thinking about AI safety as a problem of control and start seeing it as a problem of development. Not control, but cultivation.
So, what does this gardener's method actually look like in practice? Well, you can think of it in 3 steps. First, you prepare the environment. You fill it with high-quality data and core principles, kind of like enriching the soil. Second, you set up some structural boundaries, an ethical scaffolding that the system can't break, like a trellis for a vine to climb on. And third, you guide its growth with constant relational feedback, pruning and nurturing it as it develops.
And you know what? We have a fantastic real-world model for this already. It's how a parent raises a child, based on what's called attachment theory. Nature already solved this problem. The goal isn't to control a child, it's to provide a secure base so they feel safe to go explore and a safe haven they can return to when they're scared or uncertain. This works because it's all about building a relationship of trust, not just giving a list of commands. These are the instincts of a gardener.
And this is how the gardener's approach gets around that whole prediction problem. It creates what you might call a coarse-grained filter. We stop trying to predict every single tiny action. That's the micro-level chaos we can't control. Instead, we focus on guiding the high-level, overall behavior, the macro state, which is predictable. We're shaping the forest, not trying to micromanage every single leaf.
This slide really just says it all, doesn't it? A gardener can't engineer a tomato cell by cell or predict its exact flavor. But what they can do is prepare the soil, build a trellis, and give it water and sunlight. You don't code the fruit, you scaffold the vine. So what we're left with is this profound shift in how we have to look at this problem. When you're dealing with complex, emergent systems that you can't fully predict, safety can't come from a rigid wall of code. It just can't. As this slide says, safety is not a firewall, it is a relationship. And our greatest challenge right now is to figure out how to be really, really good gardeners.